Hello students, welcome to the lecture on theory of sets, and after this lecture we will be able to learn the following objectives. Discuss the basic concepts of set theory, explain the operations on sets, discuss the partition of sets, explain the Cartesian products of sets, define Venn diagrams. Let's start with the concept of theory of sets. The concept of set is fundamental to mathematics and computer science. Everything mathematical starts with sets. For example, relationships between two objects are represented as a set of ordered pairs of objects. The concept of ordered pair is defined using sets, natural numbers, which are the basis of other numbers, and they are also defined using sets. The concepts of function, being a special type of relation, is based on sets and graphs and diagrams consisting of lines and points and are described as an ordered pair of sets. Though the concept of set is fundamental to mathematics, it is not defined rigorously here. Instead, we rely on everyone's notion of set as a collection of objects or a container of objects. In that sense, set is an undefined concept. It is also assumed that sets have certain or obvious properties usually associated with a collection of objects, such as the union of sets exists. For any pair of sets, there is a set that contains them, and so on. Let us now discuss the basic concepts of set theory. The word set in mathematics was first of all used by George Cantor. According to him, a set is any collection into a whole of definite and distinct objects of our intuition or thought. However, Cantor's definition faced controversies due to the forms like definite and collection into a whole. Later on, a single word, distinguishable, used to make the definition acceptable. A set is any collection of distinct and distinguishable objects around us. By the form distinct, we mean that no object is repeated and some lack the term distinguishable. We mean that whether that object is in our collection or not. The objects belonging to a set are called as elements or members of that set. For example, say A is a set of stationery used by any student, that is, A equals to pen, pencil, eraser, sharpener, paper. B equals to Columbia, Albany, Trenton, Boston, Richmond. Here B is also a set of capital of states of USA. A set is represented by using all its elements between braces and by separating those from each other by commas, if there is more than one element. As we have seen, sets are denoted by capital letters of English alphabet, while the elements are divided in general but small letters. If X is an element of a set A, we write it as shown. There are two forms of representation of a set: set builder form representation of set and tabular form or roster form representation of set. In set builder form of representation of set, we write between the braces a variable x which stands for each of the elements of the set. Then we state the properties possessed by x. We denote this property by p, x, and separate x and p, px, by a symbol or read as such that. In tabular form or roster form, the elements of set are listed one by one within braces and one separated by each others by commas. The types of sets. Following are the types of sets: null set or empty set or void set. A set having no element is called as an empty or a void set. It is denoted by phi. For example, A equals to x such that x is an even number not divisible by 2. B equals to is the set of immortal men. Singleton set. A set having single element is called a singleton set. A equals to x such that x is present Prime Minister of Britain. B equals to 2. Finite set. A finite set having a finite number of elements, that is a set where counting of element is possible, is called a finite set. For example, A is equal to 1, 2, 4 and 6. It is a finite set because it has 4 elements. B, a null set, is also a finite set because it has 0 number of elements. Infinite set. A set having infinite number of elements, that is a set where counting of element is impossible, is called as infinite set. For example, A equals to x such that x is a set of all natural numbers. B equals to the set of all strengths in a given plane. Subsets. A set A is a subset of a set B if every element of A is also an element of B. Such a relation between sets is denoted by A proper subset B. If A proper subset B and A is not equal to B, we call A proper subset of B and write it as shown. Both signs can be negated using the slash through the sign. An example is shown on the screen. Equal sets. If the number of elements and elements of a set are totally same as any other set, such type of sets are called as equal sets. For example, A equals to 1, 2, 3, 4, 5, 6 and B equals to 1, 2, 3, 4, 5, 6. A and B above are equal sets because all the elements are precisely the same. Now moving on to the next topic, we will study the operations on sets. The four basic operations of sets are unions, intersections, complements and the Cartesian product. Unions. A union is essentially the act of adding multiple sets together to combine their elements into a single set. Look at the screen for an example. Intersections. An intersection makes a new set from the common elements of the sets involved. We have an example shown on the screen. Notice that even though A and B have 2 and A and C have 11, the intersection of the three sets is 5 as that is the only common element between all three. Complements. There are two complements, the relative complement and the absolute complement. The relative complement is the subtraction of multiple sets. The relative complement of A in B, written as shown, is the set of all elements that are in B but not in A. An example is shown here. This property does not commute. Given a universal set U, defined as containing all the elements in that area, the absolute complement is the complement of A in U and is denoted as shown. That is, a complement A complement C is the set of all elements in U that are not in A. An example is shown here on the screen. The difference of sets. Given set A and set B, the set difference of set B from set A is the set of all elements in A but not in B. Look at the screen for an example. Notice that although elements A, F, C are in A, we did not include them in A difference B because we must not take anything in set B. Sometimes instead of looking at the Venn diagrams, it may be easier to write down the elements of both the sets. Then we show in bold the elements that are in A but not in B.
Welcome to a lesson on Venn diagrams and set operations. The goals of the video are to define a Venn diagram, use Venn diagrams to show relationships among sets, and also to define set operations. A Venn diagram is a visual diagram that shows the relationship of sets with one another. The set of all elements being considered is called the universal set and is represented by a rectangle as we see here. The complement of A is the set of all elements in U, not in A. Or using set builder notation, the complement of A is the set of elements X such that X is an element of U and X is not an element of A. So if we let the universal set be the integers 1, 2, 3, 4, and 5, and A was the set containing elements 1, 2, and 3, then the complement of A would be the elements in U that are not in A, so it would contain the elements 4 and 5. So the elements 1, 2, and 3 would be inside set A, and the elements 4 and 5 would be outside circle A. Set A and B are disjoint if they do not share any common elements. So using a Venn diagram, set A and set B would not overlap. So here if the universal set was a set containing 1, 2, 3, 4, 5, 6, and set A contained the elements 1, 2, 3, set B would not be able to contain 1, 2, or 3, but it would have to contain elements within the universal set. So maybe B would contain 4 and 5. So for the Venn diagram, 1, 2, and 3 would be inside set A, 4 and 5 would be inside set B, and 6 would be outside both circles. In this diagram, B is a proper subset of A. This means that B is a subset of A, but B does not equal A. Using the symbols discussed in the previous video, we could say that B is a subset of A, and B does not equal A, therefore B is a proper set of A. And instead of using this symbol for a proper subset, sometimes you'll see this symbol here used. So if we let the universal set contain the elements 1, 2, 3, 4, 5, 6, and let's say set A contains 1, 2, 3, and 4, set B would have to contain some of the elements in set A, but not all of them because they're not equal. So maybe set B would contain 1 and 2. So we'd have the elements 1 and 2 inside B that are also inside set A. 3 and 4 would be outside set B but inside set A. and then 5 and 6 would still be in the universal set. And if we have equal subsets, that means B is a subset of A and B is also equal to A. So all the elements in A and B are in the same circle. So if the universal set was 1, 2, 3, 4, 5, if set A contains 1, 2, and 3, then in this case B also contains the elements 1, 2, and 3. So we'd have 1, 2, and 3 here, and then outside A and B would be 4, 5, and 6. So if A is equal to B, we can say that A is a subset of B and B is also a subset of A. The intersection of A and B is the set of elements in both set A and set B. Using symbols, we have A intersection B is equal to all the elements X, such that X is contained within A and contained within B. So the universal set is equal to 1, 2, 3, 4, 5, 6, and we have set A equal to 2, 3, and 4, and set B equal to 3, 4, 5. We can see that sets A share the elements of 3 and 4, so that would be in this region here. So 3 and 4 would be in this region here. And set A also contains the element 2, so there would be a 2 here. And then set B also contains the element 5, so we'd have a 5 out here. And that leaves the elements 1 and 6 in the universal set. So the intersection of A and B contain the elements 3 and 4. And now let's talk about the union of sets. The union of A and B is the set of all elements in set A or set B. So A union B is equal to all the elements X such that X is contained within A or X is contained within B. So the big difference between intersection and union is intersection we have an and, union we have an or. Using the same sets as we did for the intersection example, it would look the same, except now the union would be all the elements that are in A or B, so we'd be talking about this entire region here, because an element only has to be in one of them in order to be in the union. So A union B in this case would be all the elements in the universal set except 1 and 6, so we'd have 2, 3, 4, and 5. And a couple things to mention about the empty set. Any set A intersected with the empty set will equal the empty set, and the union of any set A and the empty set will always be the set A.
Let's now talk about the partition of sets. A set partition, S of a set is a partition of set into subsets called parts and represented as sets of sets. By extension, a set partition of a non-negative integer n is the set partition of the integers from 1 to n. The number of set partitions of n is called the nth Bell number. There is a natural integer partition associated with the set partition, that is the non-decreasing sequences of sizes of all its parts. There is a classical lattice associated with all set partitions of n. The infimum of two set partitions is the set partition obtained by intersecting all the parts of both set partitions. The supremum is obtained by transitive closure of the relation I related to J if they are in the same part in at least one of the set partitions. Look at the screen for an example. The Cartesian product. Here, before proceeding to learn about the Cartesian product of sets, we will first learn what we mean by an ordered pair. An ordered pair. A pair is a set which have only two elements like A and B. A pair can never have more than or less than two elements. It always have exactly two elements. A pair or a set of two elements in which order of its elements are predefined, or the first element is always in first and the second is always in second, is known as an ordered pair. An ordered pair having A in its first element and B as its second element is denoted by as shown here. Equal ordered pairs. As order of elements of an ordered pair is predefined, two ordered pairs A, B and C, D are equal if and only if A equals to C and B equals to D. If A and B are not equal to C and D respectively, the two ordered pairs cannot be equal. A pair AB is equal to another pair BA. For example, pairs 1, 2 is equal to 2, 1. An ordered pair AB is never equal to another ordered pair BA unless A equals to B. For example, order pairs 1, 2 is not equal to 2, 1, but 1, 1 is equal to 1, 1. Denotation of Cartesian product. The Cartesian product of two sets A and B is the set of all ordered pairs AB, where the first element of order pair A belongs to the first set A and second element of ordered pairs B belongs to set B. Note that the Cartesian products of set A and B is not equal to the Cartesian products of set B and A. Cartesian product of sets A and B is denoted by A cross B, and Cartesian product of sets B and A is denoted by B cross A. Look at the screen for an example.
The Cartesian product of two sets S and T is a set of all ordered pairs x, y, such that x belongs to S and y belongs to T. The result is itself a set and is defined intentionally below. Note that S and T are called the factors of the Cartesian product of S with T. In example 1, we consider the Cartesian product of the set comprised of the letters A and B with the set comprised of the numbers 1, 2 and 3. In example 2, we consider the Cartesian product of the set comprised of the numbers 1 and 2 with itself. In example 3, we demonstrate that the Cartesian product is not commutative with singleton sets. Note that the ordered pairs within the sets are different. A general result is that the Cartesian product of any set and the empty set is the empty set in whichever order you do it. Given the set S, we define the Cartesian nth power of S inductively. This is called a Cartesian space. Note that the Cartesian product is not associative as well. This is demonstrated below. On the first line, on the right hand side, we have a set containing a 3-tuple, and on the next two lines we have on the right hand side sets containing ordered pairs. So the Cartesian third power of S is what's shown on the second line, and neither are the expressions on the fourth line. Example 4. The Cartesian space R to the n is called the Euclidean n-space, though some authors call this a Cartesian n-space. So R squared is a Euclidean plane. Here are some properties of the Cartesian product. First, we know that it's distributive over set union, set intersection, and set difference. Next, the Cartesian product behaves with respect to the inclusion relation as multiplication does with the total ordering relation and the real numbers. So, if A is a subset of B, then the Cartesian product of A and C is a subset of the Cartesian product of B and C. Finally, for finite sets A and B, the cardinality of the Cartesian product of A with B is a product of the cardinality of the factors. This result is shown here algebraically.
If m is the number of elements in set A and n is the number of elements in set B, then the numbers of elements of A into B and B into A is m into n.
Suppose we have two sets x and y. The Cartesian product of x and y, which we denote with this symbol here, this cross symbol, is the set whose elements are all, I'm going to underline that, that's important, all of the ordered pairs of elements. Again, ordered is also important, I'm going to underline that. All of the ordered pair of elements x, y coming from these sets x and y. So small x is an element of set x and small y is an element of set y. So these are just names for elements. So let's look at an example. So we have set x, a, b, c, and set y, 0 and 1. So all of the ordered pairs pairs. So the first ordered pair we're going to pick out is A and 0. The second one we're going to pick out is A and 1. So there's an element, the first element comes from set X and the second element comes from set Y of these ordered pairs. So we have to find all ordered pairs, and there are actually going to be 6. The next two are B and 0, B and 1, C and 0, and lastly C and 1. So there are no more possible ordered pairs from these two sets. So that is the Cartesian product there. Now, just to be clear, this is not a valid ordered pair, AB, because they both come from the same set X. So that's not a valid ordered pair. Neither is 0 or 1. That's not a valid ordered pair either. Okay, so what we're going to do now is look at the opposite case. We're going to look at the Cartesian product of y and x. Now, importantly, they're not going to be the same as each other. So what we're going to do is compute the Cartesian product of y and x. I'm just going to present it here on screen now, and just to remark that it's different from what we've just done here previously. This is what we've just done previously, and the Cartesian product of y and x is that. Now, here it is important to recognize that the ordering is different. So we have 0 and A, 0 and B, 0 and C. That the element from set Y comes first in the ordered pair.
Venn diagrams. A Venn diagram is a visual representation of any given set. In a Venn diagram, the rectangle box indicates universal set U, and we can show other sets by making small circles in that rectangle box. If we have two sets A and B, then we can draw a Venn diagram for operations which we can operate on set. A intersection B is given as shown. Union of A and B is given as shown on the screen. The complement of A is given as shown here. The symmetric difference of A and B is also given as shown here on the screen. The relative complement of A and B is given as shown.
Today I will be teaching you how to make a Venn diagram. First, you need to know what a Venn diagram is. A Venn diagram is a chart that compares and contrasts two or more objects. In other words, a Venn diagram shows the similarities and the differences of the objects. To make a Venn diagram, start by drawing a circle. Remember, the circle needs to be big enough for you to write in. Next, draw a second circle, making sure to overlap part of the circles. The right side of the first circle should be overlapped with the left side of the second circle, creating a new space to write in. Next, label the objects that you will be comparing above each circle. I will be comparing cats and birds, so I wrote cats above the first circle and birds above the second circle. After you have labeled each of your circles, begin to list the characteristics of your first object in the first circle. The characteristics that you write should be differences. Don't write in the overlap part of the circle yet. This will be used later. In my circle entitled Cats, I wrote fur, paws, long tails, teeth, and pointed ears. The next step is listing the different characteristics of your second object. You write this list in the second circle, avoiding the overlapped area again. In my second circle entitled Birds, I wrote feathers, no teeth, lay eggs, wings, and ear holes. Once you have listed all of your object's different characteristics, it is time to move to the overlapped area of the circles. Here you will write the characteristics that both of your objects share. For example, I wrote that cats and birds have claws and whiskers, they are vertebrates, and both are warm-blooded animals. Now that you have filled in every space in your circles, your chart is complete. Venn diagrams are quick and easy charts that help to organize similarities and differences in objects.
Now in the end, let us summarize what we have learnt in this lecture. A set is any collection into a whole of definite and distinctive objects of our intuition or thought. A set is represented by using all its elements between braces and by separating those from each other by commas. A set partition of a non-negative integer n is a set partition of the integers from 1 to n. The Cartesian product of set A and B is not equal to the Cartesian product of set B and A. A set having infinite number of elements, that is a set where continuing of element is impossible, is also called an infinite set.